Hi there. Today we're going to look at section 1.8. It's a pretty long section, and it's the last section we do of chapter 1. So I'm going to go over some of the key points in the PowerPoints here. There's actually a lot covered, and I don't go over everything. There's some stuff on the homework that I don't go over that you have to figure out on your own, or use some of the extra help provided from the ebook or the videos in the ebook to help you get through some of that stuff. A lot of problem solving and a lot of algebra. So we're not drawing graphs by hand and that sort of thing like we did earlier. So what we're looking at here is just continuity. So continuity is the reason that calculus works. It's because functions can be continuous. And the definition, so this is the first like really technical definition. So in the PowerPoints, if you notice that I write out definition, that means you can virtually guarantee that this is going to be on an exam in some way or another. If it's in boldface, it's a vocab term, and those you have to know. But a mathematical definition is more than just a vocab term, right? When you took college algebra, you learned that a continuous function was a function that you could draw without lifting the pen or without lifting the pencil. And that works fine in college algebra. But it doesn't work fine in calculus because we have to do a lot more than just sketch graphs, right? There's a lot more going on. So look at the definition, right? It's basically saying that that as you get closer to the function, to a, that's your limit, right? Remember, this is your limit. We're saying that it equals the function defined at the point. Seems easy enough, right? So the easiest way to determine whether something is continuous is to decide if it's not continuous. And if you don't see anything that shows it's not continuous, that's actually the way you determine continuity. It's very hard to prove continuity. You basically have to use epsilon delta proofs, like we did in the previous couple of sections. And we don't want to use those proofs very much, right? Instead, what we do is we look for discontinuities. And if we can't find any discontinuities, that tells us that it's continuous. So that's the way we're going to go with this, right? Already went over that. I'll let you guys read all of this stuff. I do want to talk about discontinuities for a second here. There are three kinds of discontinuities. So the idea is that any function is continuous unless it is discontinuous. Seems like it makes sense. But discontinuities are easy to find, and that's what we're going to look at. Most of this section is dealing with finding discontinuities, and then finding places where a function is discontinuous. And then, if a function is in fact continuous, what can we do with it? That's really the only three things we're talking about. But you can do a lot with those three things, as you'll see. So a removable discontinuity just means that the limit exists, but the function is defined something differently at the point than what you would expect from a continuous function. So it could just be an open circle. It could be an open circle with a filled-in circle somewhere else in that, with that x-coordinate, right, like this. So it's called removable because you could redefine the function by just moving this here. So removable is considered the weakest kind of discontinuity. It's the easiest one to fix. All you have to do is move one point, and your function becomes continuous, right? Now there's one called a jump discontinuity. This is considered more severe, and it's because you can't just make it continuous by moving one point, right? The value of the function jumps, but everywhere else, the function is continuous, right? So notice that the limits don't exist. So go back and look at this one. This is discontinuous at a single point, and the limit exists at that point. These limits don't exist at the discontinuous points because the limits are different coming in from both sides, which prevents the limit from existing and prevents continuity as well. And the last kind is called an infinite discontinuity. This is the most severe. and it's kind of worse than the other ones because not only is it a big jump, but it's actually an infinite jump. It's a vertical asymptote. Remember, infinite discontinuity and the limit being infinity, as you approach a single value, a number, they all mean the same thing. So here's the graph of 2 to the 1 over x power. It's a really weird looking graph. And you can see that this is a very severe discontinuity. So because it's so severe, we consider it an infinite discontinuity, even if the discontinuity is only on one side or the other. Right? So you might say, well, look on the left side, it's continuous coming in from the left, but because of that infinite discontinuity on the right, it's considered very severe. So let's just jump in, and I'll let you guys read all this. So we're going to go ahead and do the first example. So left and right discontinuities work the same as overall discontinuities. Left and right limits work the same as overall limits. So you have to take what you've learned about limits and apply it here. So we're going to, we're just going to look at the discontinuities. So here's the solution page. So we identified 3 kinds of discontinuities, right? We have removable, jump, and infinite. It's always very easy to identify infinite. So let's just go from left to right. So look, our first discontinuity happens at -2. So let me just point out, this function is continuous everywhere from -4 to -2. So because the function is defined at -4, right? It's continuous from -4 to -2. Because the function is defined at -4, we say that it's continuous at -4. Now you might think, well, wait a second, didn't we just say that continuity had to have domain restrictions and limit restrictions? The domain is the most important thing. If the function is defined at that point, then the limit itself just becomes a left or right limit, depending on what we're trying to show. So -4 is not considered to be discontinuous because the function ends there, right? So -4 is part of the domain, but when you look here, -2 is part of the domain. But there's definitely a discontinuity at -2. And think about it, it's a jump discontinuity. The function does not exist from either side. I'm sorry, the limit does not exist from either side. So as you come in from the left, the limit is a number. Then the function is defined at a different number. And then as you come in from the right, it's defined at yet another different number. So this is a jump discontinuity, right? So at x equals -2, the function jumps. It actually jumps twice here. So if it jumps twice, that's still considered a jump discontinuity, okay? Then we go over here. It definitely jumps down again. Here the function is defined at the lower point, but not at the upper point. Doesn't make any difference. Still a jump discontinuity at x equals 2. So even though this one jumps twice, and this one only jumps once, it's still considered to be a jump discontinuity. Keep going. Let's look at 4. Clearly this is an infinite discontinuity. And when we get to 6, we have another one of those sort of double jumps, but it's still considered just a jump. So here's something that gives students trouble. Deciding where a function is continuous or not is a combination of, is it defined on its domain? Does the limit exist from both sides? So if the limit comes in from both sides, and those limits are different, then where it is continuous, those get parentheses. If the end point of the domain is what we're interested in, then you can have perhaps a square bracket to show that it's continuous. So f is continuous everywhere on its domain except for the discontinuities listed above. So what we do is you would just remove all of these points. So you'd say you look at its domain, you write out the domain. So the domain is from -4, but it includes -4, so that would get a bracket. And then over here, so you can see that there's no big stretches where it's undefined. It's only undefined at these 4 points. So we're only going to remove 4 points from the domain. Now, at the other end of the domain, over here at 8, notice that it is not defined at the point 8, so that's going to get parentheses. So you might say the domain goes from -4, which gets a square bracket, all the way to 8, which gets parentheses. Then you go remove. Pull out -2, pull out 2, pull out 4, pull out 6, and you get this. Right? So notice here the infinite discontinuity. We are not shown that the function is defined anywhere there, right? So look carefully at the square brackets here, right? This is squared off because the function comes down here and is defined. The function comes up here and is not defined. So this is considered to be right continuous. Up to the point 2. So that's why this gets braces. So that's something you really got to watch for. And I know that's weird. Believe me, I understand that this might seem silly. But this is the kind of thing we do in this class. We really have to understand these concepts before we move forward and start using them to solve problems. All right, moving on to the next one. So here we have a function h of t. Determine where it's continuous. So this is similar to what we just saw in the previous problem, except here we don't have the graph. We're not basing our answers on the graph. Instead, we think, what kind of function is this? This is a rational function. Rational functions are defined everywhere except where the domain is undefined. The only place a rational function is undefined is where the denominator is 0. So you have to factor the denominator, and then you find where the denominator is 0. So I just want to point something out here, guys. You might think, let's cancel these t minus 5s. Do not cancel. That was for a different type of problem earlier in the chapter, where we were trying to evaluate the limit of a function. Here, we're not interested in what the limit is at any particular point. We're not interested in the limit as t approaches 5. Here, we just want to know what is the domain of the function. So just because we canceled those t minus 5s earlier doesn't mean we do it now. Make sure that you're solving the problem that's in front of you. So this function is defined everywhere except where t equals 5 and t equals -3. And so you just write your name. You write the intervals. You write the domain in interval notation like this. So what you're going to see a lot when I present is that sometimes I use interval notation like this. Sometimes I'll use set builder notation. Those were introduced in the function review, right in the chapter, early in the chapter 1 PowerPoints, right? So that's how you do it. Right now, if you drew the graph, you would see that there is a hole in the graph at 5, and there's a vertical asymptote at -3. So the vertical asymptote is a dead giveaway that the function isn't defined there. But it's hard to see a hole in the graph, right? If you graph it on your graphing calculator, you might not even notice that little tiny hole in the graph. So we pretty much have to use algebra when we're doing problems like this, right? If you're given the graph, use the graph. If you're given the function, use the function. All right, I do want to point out some things about the theorems that start happening here and for the rest of the course. We've had some theorems, but they haven't been real serious ones. I'm going to start introducing proofs of theorems. Some of these are going to be on tests. And again, I don't want you to learn these proofs word for word, because then I know that you're just looking them up. So the proofs I'm giving in the notes are slightly different than the ones in the textbook. So if it's on a test and you give me word for word the one on the textbook, then I know you just copied it out of the textbook. So I do want you to work on any proofs that I put in the PowerPoints you are responsible for and could be on an exam. So if it says under the theorem, the proof, so sometimes I do the proof right in line, sometimes I push it to the end. In this case, I'm pushing it to the end of the slides just because the proof of this theorem is not that important for understanding the theorem. It's actually a pretty easy theorem, as you'll see. But I just want to point that out, that if I tell you that the proof is included, you have to know how to do the proof. And you should work on doing it sort of in your own way, because I don't want to see letter for letter, word for word copies if this is an exam question, right? That's kind of plagiarism, right? So I want you to do my version of the proofs, which are similar but not exactly the same. I use slightly different notation sometimes and slightly different techniques sometimes. I try not to do the exact same proofs that are in the textbook. So let's look at this theorem. Just keep those proofs in mind. We probably do 20 proofs in this class. Most of them aren't theorems. Most of the proofs we do are proofs of formulas. But early on, it's a lot of proofs of theorems. All right, so if we have two continuous functions, f and g, so if they're continuous at some point a, and c is a constant, then the following functions are also continuous. So the sum of two continuous functions is continuous. So just think about why that might be true. The proof of part 1 is at the end of the slides, okay? But think about why it might be true. The difference of two continuous functions is also continuous. Multiplying a function by a constant stays continuous. Multiplying two continuous functions together is continuous. And the quotient of two continuous functions is continuous as long as you're not dividing by 0. So why does it make sense? Let's look at this first one here. Why does it make sense that adding two functions that are continuous stays continuous? Well, the easiest way to think of it is what I told you before. You identify that a function is continuous by looking for discontinuities. If you don't see any discontinuities, then it's continuous. So the idea here is, if it's continuous, that means there's no holes in the graph, there's no vertical asymptotes, and there's no jumps. So if you add two functions together, one on top of the other, right? Like you would like with a graph. If there's no holes, you can't create a hole in a graph by adding two functions together, right? You can't create a vertical asymptote by adding two functions together. And you can't create a big gap or a jump by adding two functions together. So this should be believable even without seeing the proof, based on what we've talked about. Right? Another easy one to see is number 3, right? Multiplying a function by a constant. If there's no holes, you can't create a hole in a graph by multiplying it by a number. Like multiplying functions by numbers doesn't put holes in them, right? And if you take a function and multiply it by a number, it doesn't create a vertical asymptote. So again, this all should be believable based on what you already know about functions. Here's another theorem. We're also going to prove the first two parts of this one at the end of the slides. So the following types of functions are continuous at every number in their domains. And it's based on this, and this is based on limit laws, okay? So you have to understand this first, right? Addition, subtraction, multiplication by a constant, multiplication of two functions, division of two functions. So look at polynomials. Polynomials are just the sums of constants times power functions, right? Well, power functions are continuous, right? We saw that earlier in one of our limit laws. And combinations of constants times power functions is also continuous. And summing up a bunch of those is also continuous. And that's how we're going to prove that polynomials are continuous. So we're basing this on limit laws. All of these proofs are based on limit laws. When you first saw limit laws, you probably thought, oh man, these are dumb. I don't need these things. Because that's what I thought when I first saw this material, when I took calculus in high school. And I actually remember seeing limit laws many, many years ago. How many years ago was that? Oh, too many. I'm not counting it. And I remember sitting in class, and I had a good teacher. My teacher says, you got to learn these limit laws. And I said, I don't need these things. And then we had to do the proofs of the theorems. And I didn't know the limit laws, and I could not prove the theorems. That was AP Calc in the 90s for you young kids. So here's the idea, right? Polynomials, rational functions, root functions, and trigonometric functions are continuous at every number in the domains. So the new thing that should jump out at you is that we're including trig functions now. We haven't really talked about them much because limit laws are hard to prove for trig functions. So we really don't want to prove part 4. I just think it should be believable based on things that we've seen so far. I mean, you understand what I'm saying, right? I put, if you look at some of the review material, I gave you the graph of sine and cosine. It should be believable that those are continuous, right? There's no holes, there's no jumps, right? That sort of thing. So just think of it that way, right? If there's no holes and jumps, and if there are holes and jumps, that those numbers aren't in the domain anyway. Remember, it's easy to find numbers that aren't in the domain, like we did in the in example 2. All right, so let's use continuity. Let's do the next example. So this is very much like the sort of problem I like to put on a test because you can't just Google it. Explain why the function is continuous at every number in its domain. State the domain. And then use continuity to evaluate the limit. So what we're going to do is we're going to show that this function is continuous, and then we're going to use continuity to evaluate the limit. So remember, continuity says if the limit exists, then the limit at the point is the same as substituting that value into the function. So if our function is continuous, we are allowed to substitute pi, in this case, into the function, which would be great. All right, so let's do part 1 here. So tan x plus x squared, that's the sum of a trig function and a polynomial, both of which are continuous everywhere on their domains. So I used theorem 1.8.7 that says the sum of two continuous functions is continuous. Great. Oh, sorry, that's theorem 1.84. Theorem 1.87 says that trig functions and polynomials are continuous everywhere on their domains, and we're summing two continuous functions, right? So I'm kind of using the theorems in reverse order. Sorry about that. So again, if you want to go back and look at it, right, the following types of functions are continuous at every number in their domains, right? So this theorem says trig function polynomial. And then theorem 1.84 says I'm allowed to add those together, right? Part 1 says I'm allowed to add f and g. Because the two individual parts are continuous, I can add them together. So I'm kind of using the two theorems in conjunction, okay? Now, how do I find the domain of this? So you have to look at the individual domains. So the domain of tangent x is all real numbers except pi over 2 plus multiples of pi. And this is a polynomial. It's continuous everywhere, which means its domain is everywhere. Right? So that's what we have to do here, right? So you have to write this out. So the domain of tan x, so it's the set of all values of x where x is a real number. I didn't put that in there, but just we don't do any complex numbers in this class. X is a real number. Where x is not equal to pi over 2 plus some multiple of pi. Right? So pi over 2, 3 pi over 2, negative pi over 2. Right? It's all real numbers except that. And the domain of x squared, so the other portion here, is all real numbers. So again, sometimes you'll see that written as just a script r. All real numbers, script r, negative infinity to infinity. Those are all equivalent concepts. And I'll jump around frequently between them. So if you need help with domains, because we don't do a ton of domains in calculus, but early on we do. We do some. Get a hold of me. We can work that out. So the domain of the entire function, so the domain of this whole function is the domain of this intersected with the domain of the other one. So you take the intersection of the two domains. Well, this domain is everything, so the intersection is just this. So that's your domain. Again, you may see that as the set of all x in R, or the set of all real numbers, or something like that, except multiples of pi plus pi over 2. Now, we want to evaluate, because that's what it says here, right? Use continuity to evaluate the limit. All we have to do is plug it in, right? Oops, sorry. So this limit can be distributed, and then we can just plug it in individually. this is sort of an optional step. I just want to show you that we're still using those limit laws. And then you just plug it in, right? So you get tangent of pi plus pi squared, right? And tangent of pi is 0. And so it's 0 plus pi squared, so it's pi squared. So a lot of you might be thinking, wow, this is a lot of work to just evaluate a function. It is. We have to guarantee that the methods we're trying to use are valid methods. Because in calculus, we have the ability now, or we're going to start to develop the ability, to show that certain things are true, not just take it at face value, right? So make sure you know how to use these theorems to show that something is continuous, because I can throw any old function at you that I want. The homework tries to do this. The homework doesn't do this real great because the homework is fill in the blank and a lot of drop-down menus, and so it kind of feels sort of paint by numbers. Just understand on an exam, you're going to have to be able to do this. It's not going to be exactly this function. All right, here's another theorem. The proof for this one is very similar to what we've seen before. I am not proving this. You don't have to know how to prove this function, or this theorem. So if g is continuous at a and f is continuous at g of a, then the composite function f composed with g is given by. So we saw this in the function review. I mentioned this. And here I'm telling you that it's continuous. And again, that should make sense, right? If you have a function that's continuous, and then you use that function as the input for another continuous function, going from a continuous function into another continuous function, you should still be continuous. It's not going to create holes. It's not going to create vertical asymptotes. It just can't. So again, I want you to believe that this is true, even if it's hard to see that it's true, because it's all based on domains. Right? Just think, if these functions are continuous on their domains, then continuing to compose them creates a new function that's also continuous on its domain. All right, so let's see how to use this. This problem is similar to what we just did in example 3, except here we have radicals, right? So if you have like tangent of x and x squared, those are trig functions, and those are a lot easier to see why they're continuous, because you just know about those things. But we don't really know anything about this function, right? In fact, if you try to imagine what it looks like, you probably can't, because it's just it's called an algebraic function. But for our purposes, it's a combination of continuous functions. So we want to show that this is continuous at every number in its domain, and state the domain, and then of course use continuity to evaluate the limit. So let's look at, I'll show you what I'm about to do here. I have to break this first function down into 2 parts. I can't talk about all 3 of these parts at the same time because of how limit laws work, okay? Limit laws allow me to add functions. It allows me to divide functions. But it doesn't say anything about adding and then dividing all as a single step, right? We don't have limit laws for that. So I'm going to talk about this numerator first. Then I'm going to talk about the numerator and denominator sort of together. And then I'm going to show that it's continuous. So looking just at the denominator. So I'm starting with the denominator. That's your composition function, right? So just looking at square root of 5 plus x, that's not a function that has any sort of special name all by itself. But it is the composition of a polynomial, which I'm going to call u of x, is 5 plus x. So there's like an inside function, right? If you look at the definition of composition, see how there's like a function on the inside here? So this g of x, that's like my inside function, right? It's a function of x. F is the outside function. It's going to be a function of u, right? Because it's one domain going into a new range, and then that range becomes the domain for the other function, right? So u of x, that's on the inside, right? I mean, you can call it g of x if you want. It doesn't make any difference, but I'm just giving it a special name. Is 5 plus x, and then the root function is f of u, right? In other words, it's a function of u. The whole thing together is a function of x. right? So we start off in x, that takes us into u, and then we have a function of u, right? So we need to make sure that these domains match up. So polynomials and root functions are continuous everywhere on their domains. So that's from theorem 1.87. So here, again, this is a polynomial. I'm not looking at this as the sum of two functions. I'm looking at it as a single polynomial, right? A linear function is a polynomial of degree 1. So that's from theorem 1.87, and the composition of two continuous functions is continuous. So by composing them, by putting one function inside the other, and 5 plus x is continuous, it's polynomial. Square root of u is a radical, it's continuous. A continuous function put into a continuous function is continuous on its domain, right? We can see that this has a funny domain because it's a square root. This is a polynomial. Its domain is all real numbers. Now let's look at the two parts together. So the top is a sum of two continuous functions, right? We already know, we know how to do sums of continuous functions, right? That's from theorem 1.84. And so what we can do is add the top two, so those are continuous. Then we have a sum first, then a quotient of continuous functions. So that we're using two different parts of theorem 1.4. We're using the sum part first, that's part 1, and we're using the quotient part, that's part 5, right? But we're basically just using theorem 1.4. And here's the thing, you can't just start there because we don't know anything about square root of 5 plus x without doing this part first, okay? So I know it's a lot of work, but it's important that you guys understand why all this stuff works and how it all fits together, so later on, when you're doing more complicated stuff, you have the ability to break these problems down into what is known, what is not known, what rule should I use, what rules am I allowed to use. Calculus, the farther you go in calculus, the more different choices you have about ways to solve problems. When you guys get to Calc 2, there's going to be problems that take you 25 minutes to do, and that's knowing the answer before you start. That's just recounting the steps, 40 or 50 steps of algebra. I'm not exaggerating. So, and that's just, for some of you, you don't have to take Calc 2. You can breathe a sigh of relief. But for those of you who do have to take Calc 2, part of this process of breaking things down into what we know and what we don't know is a useful skill in and of itself. So now that we've shown it's continuous, I can plug everything in, right, to evaluate it, right? So let's find the domain here, right? Lost my mouse. So, well, this shouldn't be part B. Hold on a sec. Yeah, this shouldn't be part B. All right, so there's a typo here. I'll try to fix it by next when you guys come to this video. It should be fixed in your notes. I'm just going to go ahead and open up the calculator and show you live because I don't have it in here. So this should not be part B. This is the second part of part A here. So in the denominator we have radical 5 plus x. So that implies that x is greater than negative 5, right? Because x is not allowed, or the denominator is not allowed to be 0. So we can't, so negative 5 is not allowed to be in the domain, right? Because if you plug negative 5 into that, you get 0, and square root of 0 is 0, and you can't divide by 0. So that means x has to be greater than negative 5. We also have a square root of x in the numerator, which tells us x needs to be greater than or equal to 0. So x is allowed to be 0 in the numerator because 5 plus 0 is still 5. And then you take the intersection of those, and you get 0, infinity. So let me show you on the calculator how to do part B. All right. So this video and 1.6 are long videos. If I could figure out ways to make them shorter, I would, but I haven't figured it out yet. All right, here we go. So what I'm going to do, I'm going to do the same thing I did in previous problems, where I'm just going to put this into the to the grapher, right? So just put this in the grapher exactly the way it looks, right? 5 plus square root x. Now, some of you might be thinking, well, why not just put numbers in there and solve it? That's fine for this particular problem, but in general, a lot of calculus is plug one number in, now plug a different number in, now plug a different number in. You might as well get in the habit of using the table. It just makes these calculations easier. Plus, it's easier to see if you've typed it incorrectly because it'll look exactly like the function. So if I did this right, this should look exactly like this. Now I'm just going to go to the table, and I'm just going to type in 4, and there it is. It's already had 4 in there. So here we're taking the limit as x approaches 4, 7/3. If you use your calculators to do this, you don't have to show work for arithmetic in this class, guys, okay? You have to show work for algebra, you have to show work for proofs, you have to show work for limits, you have to show work for limit laws and continuity, but you don't have to show work for arithmetic, because there's people that can do this in their heads. Who am I to tell you not to do this in your head? So there you go. So when you plug 4 in here, so that answer is not in the PowerPoints. Hopefully it's fixed by the time you guys get to this video. I just didn't type this in right. All right, so it's 7/3, so that's the answer for part B. Sorry about that. Let's keep moving, though. So we're done with the calculator. Let me go back to full screen. All right. So the last thing we're going to look at here, so the last new piece of information is the, here it is, the intermediate value theorem. I'm not proving this theorem. I want to, but I just know there's no time to prove it. So what this is, the intermediate value theorem, is a very powerful tool that if you have a continuous function, you can really show, logically, you can use it as a powerful logical tool to draw conclusions. And so what it's saying is that if you have a continuous function on some interval, right? Notice it says closed interval, so vertical asymptotes at the endpoints are not allowed. And let n be any number between f of a and f of b, where f of a is not equal to f of b. So it's just saying that you're not allowed to have a horizontal function, okay? So look at what it says here. N is a y-coordinate. Like we had capital L for our limits, just think of it as a horizontal line, right? It's just a number measured on the y-axis, right? So if our function is continuous in the interval, then there is some number c in the interval AB. So c is on the x-axis. So that's the interval AB, right? That's not a point, that's the interval AB, such that f of c equals n. So there's a lot going on here. If you have to read this theorem 6 times, then read it 6 times. What this is saying is that we have f of a here and f of b. So look at the black line and the green line, right? We just have a function. That means any number in between here, a horizontal line can be drawn, and it will intersect the graph at least one place. And that should make sense, right? So I'm just going to kind of draw you a little picture just to kind of show you what's going on here. Right, so I'm going to use my whiteboard here. Oh, don't want that. Okay, that's my old whiteboard. I was doing some stuff earlier. I don't need a template. All right, I don't need that. So the idea here is, you know, let's say you have a function, right? And so let's say it starts here and ends here, right? And it kind of comes up like this, and it kind of comes down like this, right? Well, the idea is, if I have a horizontal line here, let me draw it a little bit better. Let's say I have a horizontal line there. is there any way that this function can be continuous? So can I connect that endpoint to that one without crossing that line? If the answer is clearly no, then you should believe the intermediate value theorem, because that's what it says. It says, I mean, it says it in reverse order, but just I have to cross there, right? Right. The intermediate value theorem says if you have a continuous function, let me do like blue here, and then you have just, you know, n is somewhere here. Is it here? It could be here. It could be here. That if you draw a horizontal line, you're going to hit the red graph. That's all it says. Maybe once, maybe more than once. So that should be believable, right? Because a continuous function, if it doesn't have a discontinuity, right? If it had a discontinuity, it could hop over that line. If it had a vertical asymptote, it could go up and come from the bottom, or it could go down and come from the top. And if it had a jump, a jump discontinuity could just jump over. But if it doesn't have any of the discontinuities, then this is very believable. So it turns out that this is actually a really powerful tool, and we're going to see how powerful it is in this example here. So we're going to show that f of x has a 0 in the interval 0, 1.3. So we have this funny function, x squared minus tan x plus 1. So what does it mean that it has a 0 in the interval? That just means that the function is equal to 0 somewhere. So if you tried to solve this, x squared minus tan x plus 1 equals 0, you have no way to solve this because you have a combination of polynomials and trig functions. We don't know how to solve that. Nobody does. But this is just asking you to show that this function equals 0 somewhere on the interval. So the way that you use the intermediate value theorem is you just check the endpoints first, right? So it says f of x takes on every number n equals f of c in the interval, where f of a is less than f of c is less than f of b. That's all it says. So if we evaluate f of a and we evaluate f of b, if one of those is positive and one of them is negative, then we're done. And let's see what happens. So what we do is we evaluate f of 0. So I'm saying that 0 is a, right? That's the left end of the interval 0, 1.3. So that's a. And you plug everything in, right? 0 squared minus tangent of 0 plus 1 is 1. Okay. So I have a positive number there. Now we evaluate 1.3. Plug it into the function, right? 1.3 squared minus tangent of 1.3 plus 1. Get negative 0.912. So what this is at 0, we have a positive y-coordinate. At 1.3, we have a negative y-coordinate. That means that for every y-coordinate between 1 and negative 9.12, if you drew a horizontal line, you would hit the function somewhere. That's all it says. Well, 0 is in between 1 and negative 9.12. So if we just let n equal 0, because 0 is in between those two numbers, that means there's some x equals c, there's some value of c, such that f of c equals 0. And that's the proof. You're done. Now again, this is not word for word the way that the book handles this stuff, right? But this is what you got to do. Can you use a graph? Sure. You could use a graph to do this as well, because you know that it's a continuous function. So if you can see that the endpoints, one's positive, one's negative, then because it's continuous, then you use the intermediate value theorem to prove that the 0 exists. But here's the thing. I evaluated this using where is it? Here it is. By typing this function, I just typed the original function into the calculator. And all I had to do was plug in the endpoints. Plugging in endpoints is actually easier than graphing, right? Because I don't have to worry about the windows and stuff. So the intermediate value theorem is actually easier to use than graphing is, right? Because all I need to do is look at the two endpoints. One's positive, one's negative. It has to cross the x-axis somewhere. That's all it's saying. Okay, so that's it for this main lesson. Oh, there we go. As normal, there's you have some extra practice stuff. There's a lot of book exercises that you might want to try. The animations and videos are very good. The homework tutor is very good. About 60% of the book exercises that I have down are shown in the homework tutor, which is pretty nice. Videos, step-by-step instructions. My versions of these problems might not be word for word. In fact, many of them aren't, but it's all basically the same stuff. And of course, you can check out the online resources. The last thing I want to talk about, the proofs of the theorems are here. I want you to read through them. I want you to learn these things. I'm not going to make you sit and watch these. These proofs are in the book. Again, mine are a little bit different. Give it an honest effort. If you have questions about proofs, you can always ask. But I do think it's important for you guys to at least start looking at proofs, because the farther we go in the class, the more important they become. So that's it for today. I'm going to fix that slide and repost this so your version hopefully is different than the one that you saw here for example 4. So that's it for today. Next video, we'll start chapter 2. And as always, if you guys have questions, let me know. Or you can post questions on the discussion forum. So that's it for today, and I'll see you guys next video. Bye-bye.